So on March 6, 2001, the Mir space station was crashed into Earth. At the time, its mass was 1.39 times 10 to the 3 kilograms. Its altitude was 220 kilometers. So we get, let's solve this one. So we have mass of the Earth. Let's write down our knowns. 5.972 times 10 to the 24 kilograms. Radius of the Earth, 6.378 times 10 to the 6 meters. Radius of orbit was 6.598 times 10 to the 6. So all I did for that one is I added that 220 kilometers. So you get 220, so 0.37 became 0.59 when I added that 220 kilometers. So what's happening in this one is we have the Earth, and the satellite is orbiting around the Earth. So here's my satellite that's orbiting around the Earth, and I decided to crash it into the Earth. So basically, up here in orbit, it is traveling in orbit. So it has the energy total is both the potential energy plus kinetic energy. However, when it finally crashes down into Earth right down there, we have some total energies equal to some potential energy plus kinetic energy. But this is not actually going to, at that point when it gets there, yes, that's speed, but it's no longer in orbit. So we're not really interested in that. It doesn't actually have that same type of value. So we don't have that kinetic energy term. But what we do have is some excess energy. So this is the energy. These two values are not going to be equal to it. The energy at the top here in orbit is going to be different than the energy down here. So that difference in energy that we're going to calculate is that energy that's going to be released when it crash lands. That's why I say like a meteorite that is traveling in space and it hits the Earth, it's going to create this large crater and create lots of damage around it if it's going fast enough. So the energy difference would be the released energy. Again, lots of that energy does get absorbed by the Earth and stuff, so we're going to get a value, but again, in real life, it's always a little more complicated. So let's see what happens. So energy total at orbit. So let's find out that the orbital energy at first. So we can use our total energy equation, negative G m over r 2r of orbit. So we're going to plug in 6.67 times 10 to negative 11, multiply the two masses. So in this case, the mass of the object was 1,390 kilograms, so 1.39 times 10 to the 3 kilograms, and divided by our orbit value. We get a value of negative 4.196 times 10 to the 10 joules of energy. Now, if we want to find the total energy at the Earth, this one we're just going to use the potential energy equation, because again, you can see that right here. We're just going to see like what is the potential energy at that point. Again, it's no longer orbiting, so we don't have that EK value. So we're going to divide by the radius of the Earth. And we get a value of negative 8.681 times 10 to the 10 joules. So we know that the energy before must equal to the energy later on. We're assuming energy is conserved. In real life, there's frictional forces as it enters the Earth, so the actual value is going to be a lot smaller. But if you say you want to crash something at the moon, because the moon has no atmosphere, this value would actually be very close to the actual value. Again, whatever we find right there is going to be a lot smaller because energy is being lost due to friction, and energy is lost at impact as well. So we end up with negative 4.196 times 10 to the 10 joules is equal to negative 8.681 times 10 to the 10 joules plus some extra energy term. So energy, like how much is lost. So we solve for that value, that E loss value. Call it whatever you want. You get a value of 4.49 times 10 to the 10 joules of energy.